This lecture will be an introduction to AC power, and we're going to consider several different types of loads or impedances that can be applied. So we're going to be thinking of resistive, capacitive, inductive, and a mixture of all the above loads. Now impedance, Z, that we know, can come in two forms. Resistive, as we know, and then something new that you haven't really seen before is reactance, and we use the symbol X for that. The reactance represents inductors and capacitors with the J operator to make them imaginary. And the resistors are real valued. And we can write a general form for the impedance where we have the Z being equal to the resistive part added to the imaginary part. Okay? And so if we have a reactance that's less than 0, where X is less than 0, that indicates a capacitive component. If X is positive, it indicates an inductive component, and when X is 0, it indicates a resistive component, because resistors are purely real. Now we can see a general load. So the circuit circled is a load. Okay, and we're calling that ZT, so it would be the impedance looking in from here as seen by the voltage source. Okay, and then we can write that general load as the combination, the parallel and series combination of the impedances. So for the resistive component, we have ZR, and it's in series with the parallel combination of ZC1, which is in parallel with ZL and ZC2, which are in series. Okay, so that's an expression for this general load, and the details of each of those impedances is given on the right. So now what's interesting is that when we solve for ZT, the total impedance, it'll always end up in the form of some real part added to an imaginary part. Okay, so this is a general formula for impedance. And so what does that look like in terms of a circuit? So it's some R added to some impedance, or some reactance actually. So if we're adding from a circuit's point of view, that looks like a series combination of a resistor, so that's the R part, the real part, and the reactance, which is the imaginary part. So that's what ZT will solve to. Now, we can map ZT as a point in the complex plane. So, we can just go over here and denote ZT with its real part. And now that real part represents a resistance value, and it will always be on the positive real axis. So it'll never be on the negative real axis. Okay? And then the reactance will be mapped on the imaginary axis, and it can be positive, and that's for inductors or inductive loads, or negative for capacitive loads. Now that's in rectangular form, and we can convert that impedance, that general impedance, into its polar form by finding the magnitude and the phase angle And the phase angle, of course, being measured from the positive real axis, either positive or negative in direction. Okay? And then we get the polar form as below. We can also solve for the phasor current, and the expression for that will be just found using Ohm's law, and so it'll just be the voltage divided by the complex impedance. Each of those quantities have their phase angles, and we're writing them in polar form, and we know when we're doing division in polar form, we divide the magnitudes and subtract the phase angles, and then we'll end up with the value for the phasor current, Im, and with the phase angle minus theta. Now, to study loads a little bit more deeply, let's look at several cases, one starting with the resistive load. Okay, and we're going to stimulate this resistive load with a phasor voltage Vm that has phase angle 0, and that gets translated to Vm cos omega t. Okay, so now since this load is resistive, there's not going to be a phase difference for the current, so the current will be described by some Im times cos omega t, so there's no phase difference between the two. And then, if we're going to calculate the power, we simply multiply the voltage by the current, so then we get Vm times Im times cos squared omega t. Okay, we've just multiplied these two together. So then, if we use the identity cos squared x being equal to 1/2 1 plus cos 2x, then we can simplify the expression for power as shown. So it's going to be 1/2 Vm times Im times 1 plus cos omega t. So now what's interesting is that this 1 makes this entire waveform positive. Okay? It lifts up the sine wave, or the cosine wave. And another interesting thing that happens is that we have doubled the frequency with this 2. Okay? So now, what does this look like in terms of what's happening with the voltage and current and the power, and what's the relationship between them? So, if we look at the waveforms, we have the waveform for I of t. Okay, that was a cosine wave. We have the waveform for V of t. That was also a cosine wave. The magnitudes here are arbitrary on the vertical scale. Okay, and then we have our power waveform, which is the expression that we found here. And what that looks like is drawn on the graph, and we see that it is a cosine wave that has been raised up, okay, and its frequency is double that of the current and voltage waveforms. So now this power waveform has a peak value of Vm times Im. Its lower value is 0, so that's 0, and then its average value is just in between those two at 1/2 Vm Im. So one thing that we can notice in this is that the power is always positive. So the power waveform, P of t, is always positive. So this means that the resistor is always absorbing energy, and when a resistor absorbs energy, that means it dissipates it as heat. Okay, that energy is lost, and we call the power in a resistor real power. Okay, So that's a definition. That's real power. So let's consider a purely capacitive load. Okay, for a purely inductive load. So in this case, the resistance value will be 0 and the reactance will be greater than 0. So what's that going to look like for us? Okay, we have the circuit on the left being stimulated by a voltage source with magnitude Vm and phase angle 0, and we have the inductor, and this is the equation for the impedance of the inductor, omega L with a phase angle of positive 90. So the stimulating waveform is Vm cos omega t as we saw before, and the current waveform is going to be Im cos omega t minus 90. So this is what the inductor does, the phase relationship in an inductor, and we can recall that we had the acronym ELI that says that the current in an inductor lags the voltage. Okay, so that's what this expression here is saying. The current waveform, because we have a phase angle of minus 90, that shifts the waveform over to the right, so that means the voltage will be leading the current, or the exact same concept is that the current will be lagging the voltage. Okay, and now to simplify this expression, we can rewrite that cosine as a sine. Okay, because if we shift cosine to the right by 90 degrees, it appears just like a sine. So what does this mean for the power? So the power is, again, same as always. It's voltage times current, and then we get a result of Vm times Im times cos omega t for the voltage part, and sine omega t for the current part. Okay, and then if we use some trigonometry, using cos x times sine x, we get 1/2 sine 2x. So then for our power waveform, we have a 1/2 Vm times Im times the sine of omega t, and what's interesting about this expression is, again, as how we saw for the resistive part, the frequency has doubled. Okay, and then what does this look like in terms of a graph? So we have the voltage waveform that we saw was Vm cos omega t. Okay, and then we have the current waveform, which we said was delayed by 90 degrees, or to the right of 90 degrees, so that's got a phase shift of minus 90. Okay, so that's represented in red. And then our power waveform, which is expressed by this equation, is shown here, and it's a sine wave. Okay, now it's a sine wave just like how the current is a sine wave, but it's got double the frequency. So we've doubled the frequency, that's why it's double. And then we have peak values for the power waveform of Vm times Im divided by 2, as we can see from the equation, of course. And then on the negative side, we have minus Vm times Im divided by 2. So one thing that we can notice here is what's happening with the power. So when the power is positive, that means power is absorbed. However, in the case of an inductor, the power isn't dissipated as heat like it is with a resistor. It's actually stored as magnetic energy within the inductor, and then when the power goes negative, that means energy is being provided to the circuit, so the magnetic energy which has been stored is being released and then delivered into the circuit. So other things that we can notice is that the average power is 0, okay, because the average of a sinusoid is 0. Another definition is that the power in an inductor is called reactive power. So this is reactive power. So it's not consumed, okay? Basically it sloshes back and forth, being stored and being delivered. Okay, so now let's consider the case for a capacitive load, a purely capacitive load. So again, we have a stimulating voltage, which is Vm cos omega t, and then we have a current in response of Im cos omega t plus 90. So what's happening in the capacitor is that the current leads the voltage, okay, and we have our acronym current leads in a capacitor leads the voltage, okay. And then if we convert the cos omega t plus 90 to a simpler form, we get minus Im sine omega t, okay. So what we've done is this cosine, the plus 90 has shifted it to the left, okay, by 90 degrees, and that becomes a negative sine wave. Okay, so then let's look at the power. So again, how we do power is voltage times current, okay, and then when we multiply those two waveforms together, we get minus Vm Im, and then cos omega t for the power, for the voltage, and sine omega t for the current. And then using the same identity we used for the inductor, we get minus 1/2 Vm Im sine omega t, with the really interesting part that the frequency has doubled. Okay, and then we have our graph. So we have our voltage as Vm cos omega t represented here. We have our current, which is leading the voltage by 90 degrees. And then we have our power waveform, which is a negative sinusoid with double the frequency. Remember, we've doubled it, so the frequency is double that of the voltage and current waveforms. And we can see from our expression that we're going to have a maximum peak value of Vm times Im divided by 2, and a negative peak value of minus Vm Im divided by 2. And then similarly to the inductor, we have when it's positive, energy is being stored. When power is positive, energy is being stored. It's being stored as an electric field inside the capacitor. And then, so it's not being dissipated as heat like it is in the inductor, in the resistor. And then, when the power is negative, that means energy is being delivered or released back into the circuit, coming from the electric field, which was storing the energy. And we notice that the average power is 0, and we define the power in a capacitor as reactive power. So it's not absorbed or dissipated, rather, as heat energy, as in the case of the resistor. The reactive power sloshes back and forth from being stored and being delivered from the capacitor. So then, now if we combine all of this, we get the idea for a general load where the resistance is greater than 0 and the reactance is not equal to 0. So reactance can be some positive number if it's inductive, or a negative number if it's capacitive. So then we're expressing the general load as a resistor in series with some reactance, and we have a stimulating voltage Vm cos omega t. Okay, and then we're representing the current as Im cos omega t minus theta, and now this is, we're going to have a special definition, and theta, what we're calling now, is the power angle. Okay, so that's an important term, and our definition for the power angle is that theta is equal to the phase of the voltage minus the phase of the current waveforms. Okay, so that's the power angle. Okay, so that's a very important definition. So theta now for us is the power angle. So then theta can range over minus 90 to plus 90. So if it's minus 90, it's purely capacitive. And what that means for the current waveform is that we have an I of t being equal to some magnitude Im times some magnitude of the current times cos omega t minus, and then we put in theta, which is minus 90. So this is something that could be confusing. So this minus is this minus, so it's separated from the theta itself. Okay, so that could become confusing. And then the two minuses cancel out to become a plus, so it becomes omega t plus 90, and it gives us our familiar relationship ICE, where the current is leading the voltage in a capacitor. Okay, and then similarly, the plus 90 indicates a purely inductive load, and then we have the expression on the right, which follows the same pattern as what we saw for the capacitor. And we can see in the end that the current lags the voltage for the inductor, and that's our familiar Eli, where voltage leads current in an inductor. Okay, so then we can repeat our analysis for power, where we multiply the voltage and the current waveforms, and we get Vm times Im times cos omega t for the voltage part, and then times cos omega t minus theta for the current part. Now, with a lot of complicated trigonometry, we can get an expression that looks like this, a big, long, complicated expression. Okay, so now looking at this expression, we can notice some things. So let's consider the average value for these terms. Okay, cos theta, that's just some number depending on theta. Okay, so that's not a changing value. However, cos 2 omega t, that's changing over time, and the average value of a sinusoid is 0. So this cos 2 omega t goes to 0. And then this sine 2 omega t also goes to 0 as an average value. So then we're just left with a simple expression for the average power, and that is Vm times Im. So those are the magnitudes, right? The magnitudes of the voltage and the current, and that's divided by 2, and then times the cos theta, where cos theta is the power angle. So just make sure that you know that that is the power angle. Theta is equal to theta v minus theta I. Okay. And so this represents the average power absorbed by the load in watts. And so if you think about it a little bit more deeply, this represents the power absorbed by the resistive component of the load. And this is an expression for real power. Okay. So now, with Vm and Im, we've been considering the magnitudes of the sinusoids, and we're going to make a relationship now to Rms values. So if you recall that for RMS, for a sinusoid, now these equations only apply for sinusoids, VRMS is the magnitude of the voltage or the current divided by root 2. And of course that becomes equal to Vm times 0.707, blah, blah, blah. Okay, so then we can rewrite that to solve for Vm and Im, so it's just VRMS times root 2 and IRMS times root 2. And then if we use the average power formula that we saw on the previous slide, then we have power is equal to the voltage magnitude times the current magnitude divided by 2 times cos theta. And then if we substitute in our values for RMS voltage and current, then we can see that the square root of 2 on both sides cancel out the 2, and then we have an expression for real power, which is also known as average power. So these are the same things. Using RMS values, we have VRMS times IRMS times cos theta, where theta is the power angle. Okay. So we have one more important definition, and that is power factor. Okay, power factor is a very important concept, and it's defined as cos theta. Okay, power factor is cos theta. And it's important to note that we can express power factor as a percentage. Okay, power factor itself ranges from 0 to 1, and we can convert that to a percentage. Okay, and so the power angle ranges minus 90 to plus 90, and something interesting is that because cos theta is an even function, the power factor doesn't give us an indication of the polarity of theta itself. So we don't know whether this theta is representing an inductive load or a capacitive load. So we need to know one more piece of information when we're given power factor. And we need to know whether it is leading or lagging. Okay? So if theta is less than 0, so if it's negative, then we say that the power factor is leading, and that indicates a capacitive load. If theta is positive, so if theta is greater than 0, then that means it is lagging, and that represents an inductive load. And we can see, the problem with theta right up here. Okay, so we have an even function. So if we're given some value for cos theta, right, it's right up here, we don't know whether it represents a minus theta or a plus theta, okay? Because the cos of minus theta is equal to the cos of plus theta. Okay, so that's a problem. So now, let's summarize about power angle. So power angle, again, it's theta minus theta v. Theta is equal to theta v minus theta I. Okay, so that's the phase angle of the voltage minus the phase angle of the current, and it ranges from minus 90 to plus 90. So if theta is negative, then the phase angle of the current is greater than the phase angle of the voltage. Okay, and then that represents a leading power factor. Okay. However, when we're talking about a lagging power factor, theta is positive, and that means that the phase angle of the voltage is greater than the phase angle of the current. Okay. So let's dig in a little bit deeper, and we'll say, what does the current do with respect to the voltage? Okay. So now, when we have a leading power factor, the current leads the voltage. Okay, So that's where the term comes from. Okay, current leads the voltage. And then we can see in our graph here, that's representing the current leading the voltage. And follows that relationship that helps us memorize current leads voltage in a capacitor. And so, of course, that means that this represents a load that is capacitive. It doesn't have to be purely capacitive, but a negative power angle or a leading power factor indicates a load that is capacitive. Okay. Now, when we look at the lagging power factor, we see that the current lags the voltage. Okay, so that is where the term lagging power factor comes from. And so now we have the graph here showing that the current is lagging the voltage, and we have our little memory aid, Eli, voltage leads current in an inductor, and of course this case represents an inductive load. Okay. So then there are some special cases. So what happens when we have power factor being equal to 1? So that means that the phase difference between voltage and current is 0. Okay, so according to our definition, power factor being equal to cos theta, and then expanded out as cos theta cos theta v minus theta I, and then the only time that we can have cos being equal to 1, which is the power factor, is when we have 0 degrees. So that means that there's no phase difference between voltage and current. Okay, and in this case, that means the load is purely real. That means resistive. Okay, so when we have a power factor being equal to 1, this means that the load is purely real or resistive. Okay, another special case is when the power factor is 0. Okay, so when we have a power factor that's equal to 0, then we know that the load is purely reactive. Okay, but the thing is, we can't tell whether the load is capacitive or inductive, okay, without more information. So we need to be informed whether the power factor is leading or lagging. Okay. Here's another visual aid showing the relationship between leading and lagging. So when we have a leading power factor, the power angle is going to be negative. Okay. And the power factor is going to range from 0 to 1. Okay. And this indicates a capacitive load. Okay. When we have a lagging power factor, then we have a power angle that is positive and a power factor that ranges from 1 to 0. Okay, so that's exactly the same as the capacitive one. So you can't tell in these two which one we have without being told more information. And the lagging case represents an inductive load. And then we have the special case down here when the power angle is 0 and the power factor is 1, and that represents a purely real or purely resistive load. Okay, so let's do a little example. Okay, so a load has a leading power factor of 0.707, which is equal to 1 over root 2. So what we want to do is find out what is the power factor, and we have to state whether the load is capacitive or inductive. So you can use what you know and try to solve that right now, and in a second here I will start the solution. Okay, so if we're solving, we have the information, we have all the information we need to determine that this load is capacitive, because we have been informed that the power factor is leading, and that means that the load must be capacitive. Okay, so now let's find out the power angle. So, what is it that we know? We know, from our theory, power factor is cos theta, and the power angle is theta is equal to theta v minus theta I. Okay, so then we've been given cos theta, which is 1 over root 2, okay, and we know that is equal to cos theta v minus theta I. And then if we take the inverse cos of 1 over root 2, that's going to be equal to theta v minus theta I. So we can see that the inverse cos of 1 over root 2 is going to be equal to plus or minus 45 degrees, which is theta, which is the power angle. However, cosine is an even function, and we don't necessarily know whether it's going to be minus 45 degrees or plus 45 degrees. But we know the power factor is leading, okay? We've been given that in the question, so the current leads the voltage, okay? So that means that the phase of the current is greater than the phase of the voltage. So, in terms of our power angle and theta v minus theta I, we know that that must be negative, okay? Because the power factor is leading, okay? So then, we know that the power angle must be minus 45 degrees. So that's the solution to that example problem. And just as a little aside, just for fun, let's look at the impedance that's defined by this example. Okay, so what do we know? So we know that, looking down here, the impedance is going to be some function of the voltage divided by the current, right? Like using Ohm's law. So we have some arbitrary voltage magnitude. We haven't been given anything, but we're going to have some arbitrary voltage magnitude and some arbitrary phase angle. So I'm just calling that theta 1. And we're going to have some arbitrary current, Im, and then what we know so far from the problem is that for whatever phase angle that the voltage is on, theta 1, our phase angle for the current is going to be plus 45 degrees. Okay, so that's the relationship between voltage and current, right? The current waveform, the current phase is going to be 45 degrees greater than the voltage phase. Okay, so then using what we know about polar arithmetic, when we're dividing, we divide the magnitudes and we subtract the phase angles, and then the theta 1s are going to cancel out, and then we're going to get some arbitrary magnitude, Vm divided by Im, and a phase angle of minus 45 degrees. And we can plot this Z on the complex plane, and our phase angle is minus 45 degrees, so that's from the positive real axis, and we have no information about the magnitude, okay? But we know the phase angle. Okay, so that was an introduction to AC power.